Alright, the second question from last weekly contest, choose k elements with maximum sum. We are given two integer arrays nums1, nums2, and for every index we are going to perform this following two steps. The first step is for all the indexes where nums1 of g is less than nums1 of I. So for every index in nums1 of I, we are going to find all the other indexes that are having lesser value than the element that we are at, and for all these indexes we are going to choose among them the k at most k values of nums2 of those indexes and try to maximize the total sum, right? So if we don't have any elements that are smaller, then we don't select any element. We have a total sum of 0 in that case. At most k is what needs to be focused here. Uh, so the first example, let's discuss that, and that should give us the intuition that we want. So what we have is 42153. There is some greedy aspect to this problem, and that should help us solve this problem. 30, 40, I'm sorry, 40, 50. Let's have index as well. Both will be always of the same size, so there is no such edge case, right? So what we want to do is create an answer of this size for every element. Like 4, we are going to select every other element which are smaller than 4, that is 2, 1 and 3 in this case. So that corresponds to indexes 1, 2 and 4, and that corresponds to values 20, 40, 20, 30 and 50. And among these three we want at most k, which is 2 in this case, so that is going to be 30 and 50, and this is going to be our answer for the first index, that is 80, right? So first thing is, we don't really want to iterate, since we can have this 5 here. Suppose we are processing this, we are finding the answer for the third index. So for 5 we are going to iterate all the other elements, right? For 1 we are going to iterate all the other elements and see if we are able to find anything that is smaller than 1. We don't want to do that. So what we can do is sort this. But if we sort this on the values alone, then we are going to miss the indexes, and that's important, because for 4 we want the answer for 4 in the 0th index only, and that goes on for all the other elements. So what we can do is we can sort both of them together like a pair, right? That is going to be 2, 1, these are the indexes, 4, 0, 3, 1, 2, 3, 4, 5, right? Now what we can do is for 1, since we know there is no other element smaller than 1, we can just add 0 to it, right, to our answer. Next thing is, by the way, we want something strictly lesser, that's why we are adding 0 and not considering the value of 1 itself, right? Now the next element is 2, right? But what if it was 1 only, right? Suppose it was 1 and this was at index 5, suppose, right? Now among these 1, we know that there's no smaller element than 1, right? So this one is going to take the answer or copy the answer of the previous one itself. So whatever answer 1 gave us, that's the same answer that's going to be for the next duplicate elements, right? And that's same, and that's true for all the other elements, right? Suppose we had another 2, we had more 3s, we had more 4s, all of them are going to have the same answer, right? Either it's 0 or it's anything, it's going to be the same answer. Only for the first 4, right? Among all the 4s, only for the first 4 we need to calculate it, others we can copy it. But how are we going to calculate the values, right? Now since we are talking about at most k elements, we want the k maximum elements, right? So what we can do is have a priority queue, and that priority queue will be a min heap. As we go on, we will have a running priority queue. So for 1, it will add the value. Since the priority queue will be empty for 1, it will have 0 as the answer. We will add now for the next element. Before moving to the next element, we will add the second index value, that is 30 in the priority queue. Then we will move here. Since the priority queue is a min heap and the size of the min heap is currently 1, which is less than k, so that's fine, we don't need to pop anything, right? So let's have a min heap value is what, 30 initially, right? Second index 30. Next thing is we move on to 1, we copy the answer to, of its previous one, since they are same, but we are also going to add the value 100 and then continue. We are going to see 2, we are going to add the value first. Before adding the value of the first index, that is 20, we are going to you know uh, find the total that we have in the min heap, but we can't do that without popping things. So what we can do is, as we push and pop, we are going to do the same operation in the current total. So as of now, the current total will be 130. We have the answer for the first index as 130, and then we are going to add the second index value, that is 30. That's going to give us 30. This is a min heap and it has exceeded the size of k. We are going to now pop the minimum most element, that is 30. We end up having 130, and that's our answer. By the way, this would have gone to 160 at this point, and then we pop 30. We are going to move back to 130, and that's it. That's how we are going to solve this problem. So sorting is going to be the dominating time complexity. That's going to be O of n log n, and space complexity will be in worst case O of n, because we are creating another array. So let's have a vector of n. Since we are going to store value and index, let's call it n1, and let's enumerate. Let's have a size, both will be of same size, both array. Let's push back in the format. The first thing is nums1 of I, that's the value, and the next thing is index. Sort this n1 dot begin, n1 dot end. Let's have a running priority queue. That's going to be a min heap. So factor of int greater of int. This is a min heap. Let's have a current total since the return type is long. So let's have that same thing here. Initially, let's have 0. As of now, let's also have a answer, since next thing is we are going to iterate and update the answer. So long size will be n for now, or we are going to push it as we go, right? Since we are going to we can process the first element beforehand itself, since for the first element is going to be empty priority queue. So what we can do is we can have the current total and the first element inside the main heap for the first processing of the element, or the whatever n1 first element is, right? So we are going to push nums, the value we are going to push, and that's going to be from nums to what's going to be the index, that's going to be the first element, first element, right? So first element of n1 of 0, and in that the first element, and the same thing is going to be the current total initialization instead of 0. Now we start iterating from the first index till the last, and for each of them we are going to check first thing first if they are equal to the previous element, right? So I can, instead of not initializing, let's initialize it, since we have processed the first element. So it's going to have zero value for the first index, and that's going to be the third index in this example, because we have sorted the n1 array, and that's why we don't know which index is the first index. So first things first, we are going to check the adjacency equality of the elements. If n1 of I minus 1 0, if it's equal to n1 of I 0, in that case copy the answer of n1 of I 1, that's the first index, the first position is the index that we are storing. Copy the previous answer at the previous index, but let's not forget we are going to process the heap, push into the heap, check if its size is greater than k, and then pop it, and then correspondingly update the current total as well. So let's have a function called process heap, which is going to take the heap by reference, take the current total by reference, take k for comparison purposes by anything, not necessarily reference, and lastly the value, and that's going to be nums 2 of n1 of I of 1, right? And let's continue. But in the other case, if they are not adjacent, not equal, in that case, you know what, let's change it a little. Instead of continuing, since we are going to process the heap anyways again, that's why let's have this in the else. So if they are not equal, then we are going to have the answer as what, as the current total, whatever the total is inside the heap, that's our answer. And then we are going to process the heap uh, and that's it. We're going to return the answer. Let's create the process heap that's going to have a min heap by reference and a current total also by reference, the value, and lastly actually k and then value. Alright, let's fix this, and we are going to push it in the heap. As I push it in the heap, I am going to uh, update the current total with this value and say and safeguard it in case if it overflows. So adding the value, if the min heap the size is greater than k, in that case reduce the value, since we are going to pop it now and the next step. Before that, let's reduce it and then pop it. Let's return back and return the answer. Let's see if this works. But since you're popping, we should be reducing that value instead, and that should be min heap dot top and not the value, right? Let's see if this works now. I think it will. The time complexity of sorting is going to dominate the time complexity overall, and that's going to be O of n log n. Space complexity will be O of n,